The equations on the left all have something in common. When we have values for x and y that, when plugged into the equation, make true statements and are therefore solutions to the equation, and graph those points on a coordinate grid, they will form a line. Notice that they are all in the same form that we call y equals mx plus b. This new equation, y equals 5x minus 3, could easily be written in the same form if we make a minor change. Instead of subtracting 3, we can refer to that as adding a negative 3. Now it's in y equals mx plus b form. So really both of them are in y equals mx plus b form. As long as we can write it in the form, we call it in y equals mx plus b form. For this equation, we don't have a coefficient of x, but we can certainly add one in there. If we have a 1 there, it doesn't change the value, and now we have an equation in y equals mx plus b form. This next equation, again, looks like it doesn't have the complete form because we don't see anything being added, but we can certainly change that by adding a value of 0. So now it looks like it's in y equals mx plus b form, but when we're adding 0 and it doesn't change the value, we normally don't have to write that. So it's okay to say just y equals negative 6x. So each of these equations on the left, when graphed in this y equals mx plus b form, will form a line. We say that they have a linear relationship. So we call this y equals mx plus b a linear relationship equation. So anytime we have an equation in this y equals mx plus b form, there's a wealth of information. This value here we refer to as the coefficient of x. That means it's the multiplier of x. That's not unique to this equation. That's just a nice way of identifying where it is, because we could even have an equation that looks like this: y equals 3x plus, or excuse me, y equals 3 plus 4x, where we can rewrite that so it's in mx plus b form, where the multiplier of x, the m value, is first, and then we have the added value at the end. So now it's officially in y equals mx plus b form. When my class first looked at this particular equation and identified that value, we described it as the growth in a tile pattern. So that's another term that we refer to that value as being the growth. It might also be referred to as the rate of change. So that would be how the values of y are changing as the values of x are changing. In reference to rate of change, we look at 2 points on a graph, and any 2 points we looked at how the x values were changing from one point to the other, and that we referred to as the run. And then the rise was the change in the y values that we identified as the rise. We found that m value was the relationship of the rise to the run as a ratio. Now, sometimes we can see on a growth triangle, we can see the rise and run as a physical growth in both values. But if we're looking at a table, we can refer to that as being the change in the y values, so the y change and the change in the x values, or the x change. As a visual, we're looking at how the vertical values are changing to how the horizontal values are changing. The last term that I'm going to write on here is one that many people are familiar with. We refer to that m value as being the slope. That's a numerical value that's giving an indication to the steepness of the line. Now let's take a look at the information from the b part of the equation. When my class was first looking at this form, we developed it from looking at tile patterns, and that value was always the number of tile in figure 0. We referred to that as the starting value. We can further identify that when x is 0, the corresponding y value is the b value of the equation. If we look at a table then, when x is 0, the corresponding y value is the b part of the equation. As a coordinate point, we can identify it when we see 0, the b value, the part that goes along with when x is 0, that b value is coming from that equation, or can be identified from that equation. That we further identified the value as, on a graph, whatever the value is when x is 0 is indicating our b value. On a graph, because it's the point where a line will go through the y-axis, we refer to it as the y-intercept, the place where the line is intersecting the y-axis, but it's called the y-intercept. So it's where that line crosses, touches, goes through, intersects, or intercepts the y-axis. Now here's a series of 4 equations. They are clearly in y equals mx plus b form, so we're going to go through and identify what is the m value and what is the b value. So go ahead and do that. You might pause the video, think it out yourself, and then progress when you are ready. So on the top left, we know that our multiplier of x is 2, our coefficient of x is 2, so that means the m value is 2. The added value is 3. Oops. So b is equal to 3. On the second equation on the top right, our multiplier of x, or the coefficient of x, is 4, so m is equal to 4. The added amount is 7, so b is equal to 7. The third equation, there's a negative 5 that's being multiplied by the x, so the coefficient of negative 5 is the m value, and the b value is the 2 that is being added. The last equation, negative 6 is being multiplied by x, and an 8 is being added for the b value. Now, it helps a great deal when we're applying this information to make a graph to have that physical rise and run value. So on each one of these, anytime my slope number, the growth, is a whole number, I know that in a growth triangle that would mean a rise of 2 and a run of 1. So any number divided by 1 is the same number, so that ratio would be equivalent to a 2 to 1 ratio. When m is 4, I know my ratio is a 4 to 1 ratio. When m is negative 5, and here it's a little bit more complex, I know that the 5 can be negative over 1, but I also know that if I have a positive 5, my run could be a negative 1. One of the values has to be negative for the value to be overall equivalent to a negative 5. That means if I go back up to the top left one, I know that if I have both of those values be negative, that would also be equivalent to 2. On the right-hand one in the corner, top, I know that both of those values could be negative because a negative 4 divided by a negative 1 is also a positive 4. So that would also be an equivalent ratio. So it just depends on which direction I'm going in my growth triangle, whether I'm going up in y values or down in y values, increasing in x values or decreasing in x values. So the last one, that negative 6, of course, either one of those values can be negative, not both of them because that would make it positive, but one of those values has to be negative to give my rise and run ratio. So each of these equations brings something a little bit unique and different to the situation. I'd like you to pause the video and try to figure out the m and the b values for these equations, and then play the video and see how well you do. So on the first equation on the top left, I don't see a multiplier of x, but I know it would have to be a 1. So that tells me my m value is 1. As a ratio, it would be 1 over 1, or negative 1 over negative 1. The b value is the 2 that's being added. The equation on the right side of that, the m value is 5. As a ratio, I know that's going to be a 5 to 1 ratio. The b value, this time I see something being subtracted, so I might need to think of what that would be if I were adding. Well, I would have to add a negative 7. Now, I generally don't think about that or even have to write it. I just look at this idea that subtracting 7 is a negative action. That negative applies to the 7, so my b value is simply a negative 7. Third equation on the lower left. This time when I'm looking at the m value, I don't see a number. I don't see a multiplier there. I just see a negative sign or an opposite sign. But I know that if I have a 1 in there, it would be like a negative 1 times x. Because if x is 5, the opposite of 5 is a negative 5, or negative 1 times 5 is a negative 5. So either way, the value would be the opposite of what it is. So my m value is the value of a negative 1. The b value, I don't see anything being added, and the only value that we can add and not have to write it would be a 0. I could write it, I usually don't, I just think about what that would be, and b is equal to 0. The last equation, it's not in that official y equals mx plus b form. I don't have to rewrite it, I just know that I look for the multiplier of x, and it has a negative in front of it, so the multiplier of x is the value of a negative 8 as a ratio, negative 8 over 1, or positive 8 over negative 1. And I didn't do that with my over here, and I ran out of room, so negative 1 over 1, or 1 over negative 1. So back to the one on the right, the b value is the amount being added. If I rewrite this equation, it would be y equals negative 8x plus 6. So I know that 6 in front is the amount being added. I generally don't rewrite it, I just know that if I change the order it would be a positive 6, or 6 being added. So now let's put this information of y equals mx plus b to use for some awesome, quick, efficient graphing. In this equation I know that my m value is 2, and my b value is negative 4. The b value of negative 4 is the y-intercept. That's where the line crosses the y-axis. So down at negative 4 is the value that I know will be on my line. It's always the first point I start at. I like that it's called the starting value as one of its names because that's the starting point when I'm graphing. I'm going to start with that point. Then from that point I'm going to apply the growth as a ratio of 2 to 1. That's a rise of 2 and a run of 1. Every time I follow that slope, I'm looking at a growth triangle. So a rise of 2 and a run of 1 is my growth triangle that I'm imagining it. Here I'm going to actually draw it, but I'm not going to draw it every time. And that gives me another point on my line. I apply that growth again, a rise of 2 and a run of 1. That gives me another point on my line. Again, rising 2, running 1, that gives me another point on my line. So when I draw my line, I know the line will go through those points. So I can, physically see my growth triangles, but I usually don't draw them. I usually just, tap on the paper to keep track of what I'm counting for my rise and run. So let's try another one. So in this rule, I know that my m value is 3, and my b value is 4. So I'm going to plot that point, and I don't think I said before, but my scale I've established at the top is a 1-to-1, just so I don't have to have those numbers in the way and try to write them on the lines on the video. It's a little bit more challenging. So my b value, I'm going to put it a positive 4, so 1, 2, 3, 4. And now I'm going to apply my slope. So the ratio of that slope is a 3-to-1 ratio. So a rise of 3 and a run of 1. Notice over here when I try to apply my slope and rise 3, I'm off of my grid. So I'm going to go in the other direction. Here's the benefit of thinking of that as being a negative 3 over a negative 1. Now I can go backwards. I can imagine going down 3 in the y values, 1, 2, 3, and a negative direction in the x values to find my second point. So it's like I'm losing tile and going back a figure number when we put it in the context of what we're doing in class. Applying my slope again, so going down 1, 2, 3 values and a run of negative 1 over to the left 1 value, I now have another point on my line. And apply that again, down 1, 2, 3, and left or backwards 1. So here's another point on my line. So now I'm going to draw the line. And there's my line that goes through those points. So again, try another one. So in this rule, I look at the coefficient of x, and I know that my m value is going to be a negative 2. This one I kind of automatically want to write that as 2 ratios, positive 2 over negative 1. And my b value, I don't see a b value being added, so remember when that happens, I know it's going to be 0. So my starting value, my first point, the line is going to cross the y-axis right at 0. That's the origin. When I apply my rise and run, so from that point I'm going to go up 2 and run 1. Now I have to decide if I need to go negative or positive. I know when I look at this rise and run as being a -2, I kind of know already I'm going to have a negative line. The y values will be decreasing when x increases. So I know that my run, when I rise 2, is going to be a -1, and that's the direction I would expect it to be heading. Apply that again, rise 2, run 1, make a point, and then from the origin point, the starting value, I'm going to go in the other direction. If I decrease by 2 in the y values, I have to increase by 1 in the x values, and there's another point. Do that again, decrease by 2 in the y values, increase by 1 in the x values, and make that a point on my line. Now I'm going to draw the line, and there I have my line. That is y equals -2x, with a negative slope and a y-intercept of 0. Okay, looking at this rule, I was looking forward to this rule. Y equals 3/4 x minus 2. I know that my growth, or slope, is 3/4. It's already in that rise-run form. If I need to go the other direction, I know I can do -3 and -4. So I'm not thinking of that as being 3/4 over 1, although it could be. But I don't want to have to count by 3/4 when I have a scale of 1, so I'm actually not going to use that. My b value is subtracting 2, so I know my b value is -2. So my graph will start at -2, or better yet, it's intersecting the y-axis. It's the y-intercept of -2. So I'm going to put my first point at -2, and then I'm going to apply that growth of a rise and a run of 3 and 4. So I'm going to rise 3, 1, 2, 3, and run 4, 1, 2, 3, 4. So I'm looking for lattice, I'm looking for lattice points. So rising 3 and running 4 will find my lattice point. If I tried to count 3/4 and go up 3/4 and over 1, I'm having to estimate where that point is. But then on the next one, it's going to be a little bit more challenging. That's not an ideal situation, but a rise of 3 and a run of 4, that will be guaranteeing me lattice points. So I'm going to go back to my last blue dot there and do my rise and run again. So from that last rightmost point, a rise of 1, 2, 3, and a run of 1, 2, 3, 4. That's where I'm going to put a point on my line. And then from my starting value, I'm going to go back 3 and back 4. So I'm going to go a rise of -3, 1, 2, 3, and a run of -4, 1, 2, 3, 4, and make that a point. Now I'm going to draw my line. And hopefully you see applying that as a rise of 3 and a run of 4 is a lot easier than trying to go up 3/4 and over 1, up 3/4 and over 1, and so on. That is just very time consuming to do that, and not as accurate, not as precise. For the final graph example, I wanted to be sure that I changed the scales up a little bit to show how important it is to pay attention to the scales. So I changed my x scale to a half. That means every line is counting by a half. So 1/2, 1, 1.5, 2, 2.5, and so on. And that, of course, is going to be the same on both sides of my x-axis. So the entire x-axis has a scale of a half. My y scale is counting by 1, so every line is going up by 1. So 1, 2, 3, 4, and so on. Even though I wrote the even numbers, I still have a scale of 1 all throughout the entirety of my y-axis. In looking at my rule, I see that my m value is -3, which is -3 over 1, or 3 over -1. Because I have a negative slope, I'm expecting my line to be going in that negative slope direction from left to right. And then my b value is a -4. So I'm going to plot my first point at the starting value of -4, and then apply my slope. So when I rise a +3, 1, 2, 3, My run has to be a -1, which is going to give me that negative direction that I want for my slope. Let me change that to blue. And then apply my slope again. So from that last blue point, rise 1, 2, 3, and run a -1. Again, +1, 2, 3 for the rise, and run 1 in the negative direction for another point. And then I'm going to draw that line. So I'm hoping you're seeing the value of and the power behind y equals mx+b, and for quick and easy graphing, no calculations, no need to make a table. Lastly, I wanted to end this on the formal name for this equation, y equals mx+b. It is referred to as the slope-intercept form for a line.